Welcome to the Heist Briefing, everyone. Today we are laying out the mastermind strategy to extract perfect marks on relative frequency in your Cambridge 0580 Mathematics Explainer. Think of this as Ocean's 11, but instead of a heavily guarded casino vault, our target is the Cambridge Examination Board, and your payload is an A-star grade. I see two types of operatives attempt this exam every single year. First, we have students like Alex. Now, Alex is a walking encyclopedia, right? Just overloading the exam paper with raw mathematical facts, writing down every formula they can possibly remember, but offering absolutely zero focused analysis. They leave fingerprints everywhere and walk away empty-handed. Then you have students like Sam. Sam is the speedster. Sam rushes the vault, totally misses the crucial command word requirements in the question, and triggers all the alarms by calculating the completely wrong type of probability. Both end up with their exam papers covered in red pen marks from the examiner. But today, we are going completely stealth. We are going to assemble your team of cognitive specialists to pull off the perfect answer heist. I'm going to show you exactly how to transform those red marks into green check marks using precision tactics. So, let's dive right in.
To pull off this exam operation seamlessly, we need to move through these 5 crucial phases. We'll start by assembling our crew, which really just means understanding independent events. Then, we navigate the deadly laser grid known as the mutually exclusive trap. After that, we're blueprinting with Venn diagrams. Phase 4 is all about decoding complex contingency tables. And finally, Phase 5 is the perfect execution.
All right, Phase 1, the crew. Let's meet the individual members of our probability crew, independent events. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, notice the sheer elegance of this formula. Independent events mean the outcome of one event does not affect the outcome of another, period. It's like a student born on June 1st and another student in the class also born on June 1st. Assuming they aren't twins, those events are entirely independent. When you see command words asking for the probability of both independent events occurring, you must use the intersection formula. The probability of A intersecting with B equals the probability of A multiplied by the probability of B. Now this is exactly where Sam always messes up. Sam sees the word both and tries to add the numbers together in a total panic. Don't be like Sam. This is where we bring in the Peel framework, adapted specifically for mathematics. Point, evidence, explanation, link. Top students structure their answers by first making their point, which means stating the mathematical rule. In this case, identify that the events don't influence each other, so we multiply.
Let's put this into practice. If you spin a coin and throw a dice, these are independent. Getting a head on the coin has absolutely zero impact on rolling a 5 on the dice. Our point is establishing that independence. Our evidence, the probability of a head is 1/2, and the probability of a 5 is 1/6. Our explanation is executing the multiplication rule, 1/2 times 1/6. And finally, our link to the final answer is 1/12. For independent events, finding the probability of both occurring is as simple as finding the product of each occurring separately. It's a clean, quiet extraction.
Moving on to Phase 2, traps. Let's see how confusing independent events with mutually exclusive events creates a deadly trap for students. The absolute most crucial point here is understanding the fundamental difference between these two concepts. Independent events can happen together. You can absolutely flip a head and roll a 5 at the exact same time. The events just don't care about each other. To find out how often they happen together, you multiply. But mutually exclusive events, they cannot happen at the same time. There is no way. You cannot roll a standard dice and get a 2 and a 5 on the exact same roll. It's physically impossible. Therefore, the intersection of mutually exclusive events is always 0. Mutually exclusive literally means their overlap is absolutely 0, while independent events simply don't influence one another. Let's see if you can spot the difference in a live exam scenario.
Here is your challenge. Let's test this with an actual past paper scenario to see if we can spot the security flaw in these numbers. We're given the probability of event X as 0.5, the probability of event Y is 0.4, and the probability of X intersecting with Y, meaning they both happen together, is 0.2. The command question asks, are events X and Y mutually exclusive? Take a mental note of your answer right now. Just think about Sam rushing this. Sam sees decimals, panics, and just guesses yes. And Alex? Alex is probably writing a whole paragraph about the history of probability. But we are going to use our logic.
And this brilliantly illustrates the correct, precise answer. No, they are not mutually exclusive. Why? Because the intersection is 0.2, meaning they can and do overlap 20% of the time. If they were mutually exclusive, that intersection value would be exactly 0. By simply stating no because the intersection is not 0, you have applied the point and explanation of the Peel framework perfectly. We bypassed the noise, ignored the 0.5 and 0.4 for a minute, and targeted the exact piece of evidence that answers the command word. But the examiner isn't done with us yet.
The follow-up question is almost always, what kind of events are x and y? Well, let's apply our formula from phase 1. If we multiply the probability of x by the probability of y, which is 0.5 times 0.4, we get exactly 0.2. Because the calculated product perfectly equals the given intersection of 0.2, we've successfully identified them as independent events. The math just proves it. This is exactly how you secure maximum marks. You don't just guess, you provide the mathematical evidence. You are proving to the examiner that you have total mastery over the mechanics of the probability matrix.
Now for Phase 3, blueprinting probability with Venn diagrams. When numbers get complicated, a visual blueprint ensures we absolutely do not double count our data.
Let's look at the math behind the visual here. The command word here usually asks for the union of x and y. This just means the probability of getting x or y or both. To find the union, we combine the probabilities of x and y. Our evidence is 0.5 and 0.4. If we add them, we get 0.9. But wait a second, if we just add them together, we've counted that overlapping middle section, the 0.2, twice, once when we counted x and once when we counted y. So our explanation step dictates we must subtract that 0.2 intersection so we aren't counting the middle zone twice. 0.5 plus 0.4 minus 0.2 gives us our final link answer, 0.7.
Stop scrolling, subscribe to our YouTube channel Ace the Exams at acetheexams_IGSC to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGSC and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, Phase 4, contingency data. Now we graduate to the heavy-duty blueprints.
Take a look at this ice cream seller's data. We have rows for adults and children, and columns for vanilla, strawberry, and chocolate. Our job is to extract specific probabilities from this matrix. This brings us to challenge 1, data scan. Imagine a 60-second timer ticking down right now. If you're Sam, you're immediately grabbing a random number. If you're Alex, you're trying to calculate the mean, median, and mode for literally no reason. But our strategy requires one crucial step before anything else. Find the outer totals. You cannot calculate relative frequency without knowing the total number of events. Let's do it.
First things first, we secure our total denominator. If we sum all the individual cells, 24 plus 15 plus 6 plus 8 plus 14 plus 28, we get our grand total of 95 ice creams sold. This is the denominator for almost every basic probability question in this entire matrix. Now the question asks, what is the probability that a random buyer is a child? We isolate our target numerator from the child row. We sum the children row. 8 plus 14 plus 28 equals 50. So we divide our target by our total, 50 over 95. But are we done? Absolutely not. Leaving it like this is like leaving your fingerprints at the crime scene.
And there is our successful extraction. We simplify 50 over 95 by dividing both the numerator and the denominator by 5, giving us 10 over 19. That right there is the simplified probability of picking a child from the group. You state the rule. You extract the 50 and the 95, you explain the fraction, and you link to the simplified 10 over 19. Perfect execution of the PEL framework. Let's run another drill.
Here is challenge 2. Find the flaw. What is the probability that the ice cream being bought was chocolate? Let's say Sam writes down 6 over 95. Can you spot the flaw? Sam only looked at the adults buying chocolate. Now let's say Alex writes down 28 over 95. Alex only looked at the children. Both of them totally failed to scan the entire data column. When the question asks for chocolate without specifying the age of the buyer, we must run another extraction, this time scanning vertically down the entire column instead of horizontally across a row.
To correct their mistakes, we simply sum the entire chocolate column. 6 adults plus 28 children gives us exactly 34. We take that target number and divide by our grand total, which we already smartly calculated earlier as 95. So the final answer is 34 over 95. It cannot be simplified any further, so we lock it in and secure the marks.
We've made it to Phase 5, execution. It's time for the final score, combining everything we've learned into one masterstroke. We are facing a massive 4x3 contingency table, detailing a delivery from a shirt manufacturer.
This is exactly the kind of question that appears near the very end of the Cambridge 0580 paper just to separate the A students from the A-star students.
Look at the sheer size of this grid. We have 3 colors across the top, white, blue, and gray. And we have 4 sizes down the side, extra large, large, medium, and small. That is 12 individual data cells. If the shirts are unpacked randomly from the delivery box, we need to be able to isolate any specific target instantly. Before even reading the question, what is our very first move? Exactly. We sum every single cell to find out exactly how many shirts are in the box. If you tally up all those numbers quickly, you get a grand total of exactly 100 shirts. Our denominator is locked and loaded.
Now for Challenge 3, Speed Writing. You have a 30-second mental timer right now. The question is, what is the probability that the first shirt unpacked is large and white? Notice the command words here, folks. It's not asking for all the large shirts. It's not asking for all the white shirts. We need the specific intersection of large and white. We need the one specific cell where these two conditions overlap. So, how do we execute the PO paragraph for this?
Bypassing all the rest of the noise in the table, we pinpoint the exact cell where the large row and the white column meet. Just let your eyes track across the L row and down the white column. They intersect perfectly at the number 10. Out of the entire box, there are exactly 10 shirts that are both large and white. We have our numerator. We have our evidence.
Let's write up the final explanation. Step 1. We located the L row and white column intersection, which is 10. Step 2. We already summed every single cell to find the total box contents, which is 100. Step 3. We construct the probability, the target over the total, 10 divided by 100. But a master thief never leaves a messy scene, right? We simplify. 10 over 100 simplifies beautifully to 1 over 10. By systematically finding our specific target and dividing it by the total contents of the delivery box, we've perfectly executed the calculation. You've hit the command words, you've extracted the exact evidence, explained your working, and linked to a perfectly simplified fraction.
Let's review the unwritten rules of our operation to ensure you leave absolutely no marks behind in the exam hall. This is your ultimate cheat sheet. Rule 1. Command word decoding. If they are independent events, you multiply the probabilities. If the question asks about mutually exclusive events, you check if the intersection is exactly 0. Rule 2. Peel framework application. When dealing with unions, remember to subtract the overlapping intersection so you don't double count. State your point, extract the evidence, execute the formula. Rule 3. The time management matrix. When you see a contingency table, don't waste time panicking. Immediately find your outer totals first, then isolate your specific row, column, or intersection. This system guarantees top marks and keeps you from turning into an Alex who overthinks, or a Sam who rushes and misses all the details. Students who implement these calculus mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos.
With these formulas and visual strategies mastered, you now have the ultimate blueprint to tackle any relative frequency challenge. You bypass the traps, isolate the targets, and extract the perfect answer. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at @AceTheExams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @AceTheExams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. Keep thinking logically, keep studying smart, and I'll see you in the next explainer.